Okay, so question number 2 is also a Lewis structure question. The following Lewis structures for hydrogen cyanide, ethylene, tin oxide, and boron trifluoride, and so on, are incorrect. Explain what is wrong with each one, and give a correct structure for the molecules. This is an interesting take on the Lewis structure questions. So let's start off with writing the wrong molecule, just so that we can compare it and see what's wrong. So it's supposed to be a molecule of HCN. So let's start off with writing all the total valence electrons in the molecule. So hydrogen has a valence electron of 1, carbon is 4, and nitrogen is 5. So if we add it all together, we're only supposed to have 10 valence electrons in this molecule. So if we count it out with each bond containing 2 of them, we have 6 in the form of bonds, 7, 8, 9, 10, 11, 12. So this molecule has 12 electrons. So if we were to draw the correct version, this lone pair of carbon, I'll turn it into a bond. And the nitrogen should only have 1 lone pair. So you'll notice that the carbon still has a full octet, and you'll notice that the nitrogen now just has a single lone pair. So if we count out the total valence electrons, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is the correct structure. Okay, so now let's check out what's wrong with the next molecule. Okay, so already looking at it, each hydrogen has a double bond. So I'll just say hydrogen shouldn't have a double bonds. This is because it only has 1 electron available to share. So you'll never see hydrogen having a double bond. So now let's try to find out how many electrons are supposed to be in this molecule. We have 2 carbon atoms, each with 4 valence electrons each, and we have hydrogen with 1 electron each, but there are 2 of them as well. So we're only supposed to have 10 electrons in this molecule. And the one on the left also has more than enough, so it has like around 12. So let's draw the correct structure with single bonded hydrogens. The carbon will still have a double bond, or actually it should have a triple bond now, so that it would have a full octet. And then the last carbon also has a single bonded hydrogen. So if we count out all the electrons, there are 10. So this structure is now correct. Okay, so the next one, we have 2 single bonded oxygens to tin. And now let's count out how many valence electrons are supposed to be in this molecule. So tin has 4 valence electrons. For oxygens, it'll be 6 times 2. So that leaves us with 12, 13, 14, 15, 16. So we need 16. And if we look at the incorrect molecule, you'll notice that tin doesn't have a full octet. So I'll say SN doesn't have a full octet. And if we count out all the electrons in this molecule, there are only 12 when we need 16. So let's try to write the correct one on the right. For tin to have a full valence, to have full octet, I'll draw these oxygens as double bonds instead, and then just write down the remaining lone pairs. Yeah, and in the old molecule, both of them don't have a full octet, so that's why extra. And now if we count out all the electrons in this molecule, you'll see that it is now 1, 2, 3, 4, 5, 6, 7, 8, 16. Okay, so let's start a new page and go to the next molecule. We have boron that is attached with 3 fluorine atoms, and it also has a lone pair. So let's calculate how many valence electrons are supposed to be in BF3. So for boron has 3 valence electrons, and for a fluorine atom, it has 7. And there's 3 of them, so 21 plus 3 is 24. So if we count out how many electrons are in this molecule, you'll see it goes over that. So this has 26 electrons. So let's write the correct structure on the right. So with molecules containing boron, boron is one of the exceptions to the octet rule. So it's actually satisfied even with just 6 valence electrons. So I'll write that down. That boron is an exception to the octet rule. And now if we count out our electrons, we should have 24 in this new structure. Okay, so now moving on to E. Already you can see that something is wrong because the fluorine has a double bond. And typically it's not that common for fluorine to have a double bond. And you'll notice that it has more than a full octet as well. which is unlikely, so I'll just say fluorine has more than 8. And we have 14 here, but let's calculate how much electrons we're supposed to have. So for hydrogen, it has 1 valence electron, oxygen has 6, and fluorine has 7 that participates in the bonding. So if we add it all up, there are 14. So let's try to draw the correct molecule. So instead of fluorine having the double bond, we are going to keep it as a single bond and just have 2 pairs of lone pairs on the oxygen, and we should still have 14 valence electrons without the fluorine being like oversaturated. Okay, so this is the correct structure. And now let's look at the last molecule. And let's try to see how many lone valence electrons it should have. I don't really know the order that this molecule should be in, but anyways, carbon has 4 valence electrons, hydrogen has 1, oxygen has 6, fluorine has 7. So if we add them all up, we should need 18 valence electrons. So if we look at the incorrect structure, everything seems fine except for the oxygen, which is not satisfied. So let's count out how many electrons are in the molecule. 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So there's still 18. But instead of the lone pair on the carbon, I'm going to convert it into a bond, another bond with oxygen to have a double bond. And now we should still have 18 electrons, only now the oxygen has a full octet. So this structure is now correct. So let's compare answers with the junior tutor, starting from the first page. So HC double bond N. So the total number of valence electrons in the given Lewis structure is equal to 12. The actual number of valence electrons for HCN is 10. Therefore, the correct structure is the carbon with a triple bond. For B, the total number of valence electrons in the given Lewis structure is equal to 12. The actual number is equal to 10. So valence electrons, therefore, 10 valence electrons. So therefore, the correct Lewis structure is the triple bonded carbon. Next, the octet rule is not satisfied for any of the elements, and the number of valence electrons for this structure is equal to 12. Actual number of valence electrons is equal to 16. Therefore, the correct Lewis structure is just contains double bonds instead of single bonds. For D, this Lewis structure has a total of 26 valence electrons. Actual number is 24. Boron is an exception to the octet rule. It is satisfied with having 6 shared electrons. Therefore, the correct Lewis structure has the boron without containing an extra lone pair. So for E, this Lewis structure has the correct number of valence electrons, 14, but the fluorine atom has more than 8 shared electrons. Fluorine is in period 2, so it cannot be hypervalent. Therefore, the correct Lewis structure is... So by hypervalent, these can be elements that can have more than 8 shared electrons. So they're usually found in the transition metals. And then lastly, F, the number of valence electrons for this Lewis structure is correct, 18. But the octet rule for the oxygen atom is not satisfied, and it only has 6 valence electrons. The correct Lewis structure is the following, that has now a double bonded oxygen. So this solution is correct.